my pleasure now to introduce another very close friend, former neighbor of mine in Bluebell Avenue in Boulder, Dr. Franklin Roach, affiliate astronomer, University of Hawaii, and research associate in astronomy at the Battelle Northwest in Richland.
Thank you, neighbor. Most of the UFO reports refer to some kind of a sighting in the sky. Astronomers feel, perhaps without justification, that the sky is their domain. Therefore, UFO reports and astronomers have a natural confrontation. The speculative interpretation of some UFO sightings as due to terrestrial visitations by non-terrestrial intelligences is usually a cause for dismay on the part of astronomers because they appreciate the enormous distances involved in the transport between ports of call. The interest in UFOs has had a very good effect. Quoting Professor Page, who just spoke, quote, "Student interest in a topic, even if it derives from misconceptions, is better than no interest at all," end of the quote, which I would paraphrase to say, to rephrase in the following way: the end justifies the means. But I think there has been another educational feature, namely the education of all of us, because we are all students, are we not, that the interest in this speculation about the non-terrestrial origin of UFOs has really stimulated a healthy interest in the problem of extraterrestrial intelligence in our galaxy and in the universe. And I think this is an excellent thing that the public and all of us have perhaps departed somewhat from our homocentric point of view and expanded our imaginations because of this excited interest. And again, they have justified the means. About 8 or 9 years ago, a multidisciplinary group of 11 scientists who were dubbed partly by themselves, I take it, the Order of the Dolphin, and one of whom is here now, met to discuss something about the quantitative aspects of extraterrestrial life, and they have suggested a formula, first slide please, to tell us something about the probability that we are being signaled, at least, from some other civilization. This is one way of writing down the formula, in which N is the number of civilizations capable of communicating with us, and L, which is a very important parameter, the lifetime in years of each civilization, and D, which I have added in the bottom row, the distance to the nearest civilization to us in light years. And here is my compilation there, where I have used my own criteria of pessimism and optimism in the first and the third columns. I think it's quite pessimistic to say that the lifetime of a civilization is only 10 years, 1 decade, and if this is because we have actually managed somehow to survive as a civilization with technological abilities more than a decade, although sometimes it has looked a little bit dubious whether we could continue too much longer. But if this were the case, then the distance to the nearest civilization in light years now, at this moment, would, in our galaxy, suggest that we really are essentially alone as a civilized race. Over on the far right-hand column, I have put an optimistic estimate, and the first time I made a slide like this, I put 10 to the 10th for optimism, but I've become a little more pessimistic since that first slide, and I've now reduced it to 10 to the 7th years, which is 10 million years. And in that case, the number of such civilizations would be 10 to the 6th, and the distance to the nearest one to us would be something like 140 light years. And the middle column you may take as a balanced one between pessimism and optimism, if you wish. The next slide, please. The problem of intercommunicating, or certainly of intertravel between stars, is suggested by this slide, in which the nearest stars to us, to our sun, are indicated here in a two-dimensional plot, and the nearest star to us being about a little less than 5 light years, or a little more than 4 light years away. I call your attention to that very interesting star Barnard, 6 light years away, because it has been established that there are one or possibly two planet-like objects going around the star, Barnard star there. And you see the other stars. I also call to your attention the two stars. Is there a pointer, Walter? Calcete, at about 10 light years, Epsilon Eridani at a little more than 10 light years distance, which are two stars which were looked for, toward which we looked in a Project Ozma, not we, but the human race, in which an attempt was made to see if by any chance we were being signaled from these two stars. The enormous distance of even that inner circle of 5 light years is what has given pause to most astronomers when they think about the possibility of interstellar travel, and I think Professor Sagan will discuss this particular point in his lecture tomorrow. The distance is so enormous that most astronomers, I think, would tend to agree with analyses such as that of Professor Markovits, who indicates that the problem is not one of physics but of metaphysics, which in his interpretation means magic. Next slide, please. Now, I have been intrigued with the idea that if we had lived in another part of our galaxy, perhaps in the center of a globular cluster, such as this beautiful one, the Messier 13, or the cluster in Hercules, the stars would be so much more closely packed that perhaps travel between civilizations within that kind of a domain might be more readily possible. And I show you now on the next slide something about how far apart we might expect stars to be if we were in that position, in the center of a globular cluster. You see in the lower left hand that the mean distance between objects in such a part of the galaxy is about 3/10 of a light year. Can you see it from where you're sitting? Yes. In the center of our galaxy, it's about 1 light year mean distance. In the vicinity of the sun, where we are, it's almost 7 light years average distance between stars, and the nearest one actually is a little over 4 light years, Alpha Centauri, and here you see the results here. By the way, the ordinate here is light years. A little later I will change to a much more interesting orbit from the standpoint of the Apollo program. Next slide, please. I have done some interesting calculations which have implications more in the astronomical side than in the UFO side. But here I have plotted the space density, the number of objects in a given volume, in this case the volume being the cubic centimeter for convenience, and it made a very interesting interpolation between stars, and the space density of stars is shown here, and galactic dust, which is something which we also can observe because of its obscuring nature. And the interpolated region includes objects of masses less than stars, but greater than dust. In here would be comets, asteroids, objects such as planets in mass, which might be in interstellar space. And this corresponds to the density in the general region of the sun, but not specifically associated with our solar system, the interstellar density in our part of the galaxy. And I was interested in this curve because I wanted to get an estimate of the density of such objects as are heavier planets, such as the planet Jupiter, for example, because of the imaginative and highly speculative suggestion of Harlow Shapley some time ago that the internal heat from massive objects, such as a Jupiter-like object, which might be sufficient to nurture life on the surface, even though such an object were wandering between the stars and did not have the beneficent light of a star, such as our sun, to give it heat. Of course, the spawning of life on such an object would have to be without the benefit of photosynthesis, and the chemists don't like this. The biochemists don't like it. I was sailing off Waikiki the other day and suggested this to a biochemist who was aboard, and he looked at me like he would like to throw me into the drink, and I'm a poor swimmer, so I quickly changed the subject. However, it is interesting astronomically, what is the density of objects such as Jupiter, 1/1000th the mass of the Sun, where this is 33, 10 to the 33 in grams, which comes somewhere in here in the curve, and Jupiter-like objects wandering around in interstellar space. And we will proceed to discuss that point now. Next slide, please. Here is a plot transferring that density, which I just mentioned, into the number of such objects, Jupiter-like objects here, lower curve, Earth-like, Moon-like, and like the asteroid series here, against the distance from us, from the Sun, in centimeters. And I should say that this vertical line here corresponds to halfway to Alpha Centauri, which I would define as a kind of a solar domain. This is 10 to the 7th times the distance to the Moon, 10 to the 6th, 10 to the 5th, and this vertical line here corresponds to the distance to our outer known planet, Pluto. And this being a logarithmic scale, this is log 0 corresponds to 1. You see here, within the solar domain, there should be significantly more than one Jupiter-like object, and actually the number is 7 when you go from the logarithmic to a linear scale. Out in this domain that I'm talking about, out to halfway to Alpha Centauri, is the domain that Jan Oort has suggested contains a swarm of objects, comet-type objects, some of which come in close to the Sun when their more or less circular orbits are perturbed, and they have very eccentric orbits which bring them in close to the Sun. You can do a little bit of statistics and find that of these 7 Jupiter-like objects, over a period of 5 times 10 to the 9th years, 5 billion years, we might expect that one of them might be perturbed to come in relatively close to our Sun in astronomical time. So I'm going through an interesting speculation here about this, the possibility that such an object might, with its period of some millions of years, spend a few thousand years relatively close to the Sun and might be picked up in an astronomical search. Next slide, please. If such an object does exist, then here are some of the properties of the same. I've taken these 3 distances here. This is about, you see, 6 times to Pluto, 60 times, and 600 times the 3 distances which I chose for calculation purposes. From the planet X, the brightness of the Sun would be very great here. By far the brightest object in the sky, even is here, and a very bright object here. This being about as bright as Venus is to us at the brightest. The brightness of Jupiter, on the other hand, would be, as seen from this planet at these distances, significantly fainter, and might be very difficult to see with respect to the Sun unless one had a pretty fair telescope. From the Earth, however, the brightness of this planet would be at this distance, some 6 times the distance of Pluto, magnitude 13, and should be easily measurable and detectable by ordinary techniques from our telescopes. But going out 10 times as far, the object becomes magnitude 23, which would be extraordinarily difficult to detect even with a very large telescope, and in the outer part here, impossible by any conceivable telescopic techniques. This suggests that the astronomers might look for an object, although maybe not this year, maybe not next year, but maybe a million years from now, such an object might be brought in astronomically. Now I should warn those of you who may be trying to extrapolate from these comments that this might be the source of UFO visitations, because there is a speculation on a speculation here. The first speculation being that life might have developed on such a planet, and the second speculation that this particular planet was made into an eccentric orbit which came in close enough to have sent out a messenger to us. In any case, I administered the astronomy of this particular problem. Next slide, please. The astronomers always stress the enormous distances involved in this interstellar problem of travel, but not as often perhaps the enormous times within which one must consider such possibilities. And here's a plot in which I call your attention especially to the abscissa, the lifetime of stars corresponding to these densities in space. The cooler stars live longer. They're not so profligate in their expenditure of energy into the 10 or even 100 billion years here, and there are many more of them. A continuation of this idea has just been suggested when I discussed the possibility of finding these Lilliputian things, as Shapley called them, namely the objects which are not massive enough to be stars, but are massive enough to be perhaps warmish planets. So we have a long, long period of time beyond our finite comprehension, I think, to really do more than put numbers down on plots in terms of the times involved and the times that are available to us for consideration of travel. And I have suggested perhaps a little bit facetiously that the metaphysics or magic of Markovits should be changed to megaphysics, the physics of a million years hence here, or the physics of a civilization which may be a million years ahead of us. Next slide, please. I rather facilely use the expression million years, and one's first reaction, of course, is that a million years is a tremendously long time. Actually, relative to astronomical times, a million years is an extraordinarily short time, so that we must adapt ourselves to the fact that a million years is an astronomical flick of time, and this is more for the students than for here. This is a logarithmic scale going over 10 to the 10th, and here you see how the logarithmic scale has to be broken down into a series of linear scales in order to understand, for example, 1 million 10 to the 6th compared to 10 to the 10th. On this scale here, 1 million years is here, but on a linear scale, if you start out with 10 to 10th, it's much, much less than the thickness of the drafting pen as it's drawn there. I'm recalling now a meeting, a social meeting, early in the Colorado Project, when Dr. Hynek summed up his attitude at that time as saying, I am puzzled, and my reaction at the time was, I am curious. I'm curious to know why Dr. Hynek is puzzled, and this led me into the project. And I would say that this is still my attitude. I'm still curious as to what this is all about. My interest is primarily in the direction of the extraterrestrial possibilities, but this is perhaps only one side of the picture. Next slide, please. The question that is asked is the following often: if there is anything objective in these sightings, why don't the professionals make reports? And so I would make it much more personal, since I've been a professional observer of the sky myself for a third of a century. Why haven't I made reports? And it's a part of the set, if you wish, of an observing astronomer, that when he sees something, when I see something in the sky, my foot goes automatically in seconds. I'm counting seconds with my feet. I quickly look at my watch to get the time. I try to see where the object goes from one place in the sky to another with respect to the constellations. And so what I'm trying to say is that I have a bias, because immediately I am trying to interpret such an object in the astronomical sense. And now I realize that I am unusual in having a bias. Most of you are completely unbiased, but I do recall that someone said that some of our television commentators, these paragons of objectivity, could open a telephone book and read half a dozen names with a deadpan face out of the telephone book, and by a little flick of the eyebrow would imply something about the character of these people that they're reading about. This is too bad that we have these very biased people in the television industry, and it's very nice to talk to an audience of completely unbiased people, but I have to confess that I have the astronomical bias in this whole investigation. This table here is from Thornton Page, and he did allude to it in his discussion, in which he shows that the telescopes of the world, the professional telescopes, and the important thing is over here in terms of n times c, where this is the product of time and space coverage, and it represents the fractional coverage of a 30-degree cone centered on the zenith, and it is here 14.56 times 10 minus 3, or about 1.5% is the coverage of all of the busy astronomers around this planet who are observing the sky and photographing the sky, and so it's a relatively small percentage. Let us go to the next slide and see what other kinds of sky coverages there are, in addition to the astronomical photography, which Professor Page had analyzed in connection with his class. Here are some of the meteor networks, the prairie networks in the prairies of this country, which Page has discussed, Ayer has discussed in the Colorado Report. Clyde Tombaugh made a very systematic search for terrestrial moons and for trans-Neptunian planets. He, in the course of his work, discovered the planet Pluto, as you remember, and he would have picked up anything as faint as magnitude about 15 or so. In particular, he would have picked up a Lilliput coming in as close as the one which I said at 4 times Pluto's distance. I have been concerned with the number 5 here, the airglow scanning photometers, and so I, on the urging of Dr. Condon, did make an analysis of one night of observations and looked and asked myself the following question. Are there any blips, any deflections on the record which I cannot explain as due to a star or a planet? Now, I said this in first person I. Actually, it was thought advisable because of my bias to keep me off the direct investigation. So Dr. Ayer did it, but I suggested the way he should do it. Next slide, please. Here is a comparison of the prairie network and the airglow photometers. I'm going to discuss this from here. It would be nice if some of the prairie network people could discuss this. The last entry here shows you that if you found a particular object of UFO or UFO interest in the prairie network, this would be, you should multiply by 1,500 to indicate how many there would be in total. And the airglow photometer section is much less good coverage. We should multiply by about 250,000 in order to normalize a single observation in terms of the totality of what you might expect. Next slide, please. This is the kind of record that I have been working with for, as I said, a third of a century. I think that sounds more impressive than, say, 33 years. Here's an old record which I took at the foot of Mount Locke in 1934. And here this gives an example as you go around in what the astronomers call an almacanter. You cross a star, you get a blip like this. There's the beautiful zodiacal light. There's the Milky Way, another star, and so on. The question is, are there any blips on the records like this which are unidentified? So we took a night where we had records of this sort at Haleakala in Hawaii, a fairly recent record, the beautiful sky, photometric sky, and instead of just saying we're interested in the zodiacal light or the Milky Way, we identified every blip. We did this with a machine because it was a very large job, and when we got through, we found 2 blips which we could not identify as stars or planets, nor anything else that we knew. And so in the Colorado Report, in Dr. Ayer's chapter, you will find the mention of these 2 UBOs. So, the light, please. I must say, that in this particular case, a night chosen at random, we found 2 unidentified objects, but the trouble is, all I can say is it corresponded to a second magnitude star, and so we are limited in the information we get. And this is the problem in such objective type studies. If we adopt Dr. Hynek's suggestion of plotting strangeness and reliability, this is a very reliable observation. The only strange thing is that we can't identify what the observation means, and I suggest that part of the reason for this is that strangeness depends upon the nature of the observation. If the observation is made by a machine, you are not likely to find strange results. If it's made by a person, then the strangeness criterion is likely to become very important. Thank you.
Thank you very much, Franklin.